Hey everyone, and welcome to today's Explainer. We are diving into a technology today that's literally poised to rewrite the entire rulebook on additive manufacturing. It's called solid-state UV cross-linking based volumetric additive manufacturing, or AVAM for short. Now, if you're used to traditional 3D printing, the kind that needs a perfectly stable, highly controlled lab environment, this is going to blow your mind. We're stepping completely out of the lab and into some of the harshest, most unpredictable environments imaginable. So picture this for a second. You're trying to use a traditional, messy, liquid resin 3D printer on a naval vessel crashing through ocean waves. Or think about trying to print a critical replacement part in the microgravity of a space station. There's just no way, right? The liquid sloshes around, it's incredibly unstable, and it's basically a disaster for precision. So how on earth do we manufacture crucial parts on the fly in those kinds of dynamic environments? Well, the answer is actually pretty simple. We get rid of the liquid. Traditional SLA, stereolithography, is fantastic, but it's completely chained to that liquid resin vat. It's super sensitive to vibrations and liquid level fluctuations. SVM completely flips the script. Instead of curing a liquid, it initiates the UV cross-linking reaction while the material is already in a solid or semi-solid state. We are essentially replacing the fluid, unstable past of 3D printing with a solid, hyper-precise future. Here's a quick look at how we're going to break this down today. First, we'll look at the solid-state revolution, then the core advantages of SVAM. After that, we'll dive into key lab research, the materials making this possible, the incredibly cool shape memory effect, and finally, future challenges. All right, let's jump straight into part one, the solid-state revolution. The core concept of SWAM is just so elegant. Instead of shooting lasers into a pool of liquid, it initiates UV cross-linking reactions entirely within solid or semi-solid materials. By totally eliminating liquid flow, it completely solves the inherent flaws of previous 3D printing generations. No sloshing, no gravity-induced flow interference during the print, which means we no longer need those massive, bulky shock absorbers that traditional printers absolutely rely on. Moving on to part two, the advantages of SVM technology. This tech brings some major game-changing benefits to the table. First up is portability. Because the material is solid, the equipment can be incredibly compact, which is perfect for space missions, aviation, or maritime use. Second is high precision. Without liquid flow messing things up, we can achieve micron or even nanoscale structures. Third, it's fast. Solid-state reactions are generally much quicker. Fourth, it can create complex 3D structures that traditional FDM or SLA just can't handle. And lastly, any unused surrounding material can just be removed, reshaped, or reused. It's super efficient and allows for incredibly flexible workflows. Section 3, Key Lab Research Breakthroughs. Let's look at the real-world evidence. To prove that you don't need massive, expensive machinery for this, researcher Ivan Lee created a highly portable 2D solid-state UV system using a modified NEJ laser engraver controller board. He tested 4304 resin and H1106 polymer, finding that H1106 was way more promising for both speed and resolution. Building on this, another researcher, Dennis Lim Wei Yi, pushed things even further with a dual-beam solid-state setup, proving you could maintain consistent curing across multiple exposure positions, essentially simulating an assembly line process. Then, researcher Lo Feng Rong tackled another massive hurdle, preventing the solid resin from sagging under its own weight before it's fully cured. In regular room air, the resin tends to deform, but when he submerged the entire setup in 5 degrees Celsius cold water, the water provided absolute thermal and physical stability, allowing the resin to cure perfectly and uniformly in just 8 seconds. Honestly, talk about a breakthrough. Let's look at part 4, the materials making it happen. Researchers have been testing some absolutely fascinating photosensitive materials, usually adding DMPA as a photoinitiator and hitting it with a 395 to 405 nanometer UV light. We've got H1106 resin, which needs that cold water environment for stability. Then there's Pluronic F127. This is a thermal gel that's solid at room temperature but melts when cooled below 10 degrees Celsius. That means you can print a solid object and literally just wash away the uncured support material with cold water. And finally, there's UPY HTBP UPY. This UP polymer is incredible. It's a Vitrum-like polymer, meaning it sits somewhere right between a thermoplastic and a thermoset. At room temperature, it's a solid held together by dynamic quadruple hydrogen bonds. But when you expose it to UV light, it forms permanent photo crosslinks. So basically, you can mold it like clay at room temperature and then blast it with UV light to permanently lock that exact shape in place. Okay, Section 5, the shape memory effect. Now here's a major challenge. When you separate the newly cross-linked, fragile parts from the surrounding uncross-linked solid block, they often bend or severely deform. If they stay bent, your print is ruined. But thanks to the shape memory effect, or SME, the material essentially remembers its original programmed shape. When triggered by a specific stimulus, like heat or water, it physically undoes the deformation. The programming procedure for this is super cool to think about. Step 1, the material gets deformed, maybe accidentally during extraction or maybe on purpose. Step 2, you freeze or cool it down to lock in that temporary deformed shape. Step 3, you apply the stimulus, like submerging it in hot water. And step 4, the material physically recovers its original cross-linked shape. Lab tests show this happening in real time, and it's practically magic. Researchers took a completely bent, deformed, cross-linked resin rod and dropped it into 100 degrees Celsius water. In just 45 seconds, the rod literally straightens itself out, recovering its original shape with over 97% accuracy. It is an unbelievably elegant solution to the deformation problem during solid-state separation. Finally, Section 6, future challenges and industrialization. We've got to be real, there are still some engineering bottlenecks before this hits mass production. A lot of it comes down to the physics of light inside solids. We've got light penetration depth limits. Energy decays as it travels through solid material, limiting how deep we can actually cure. Then there's the light halo effect, where unwanted light scattering cures resin where it shouldn't, which ruins dimensional accuracy. To move from the lab to the factory, we urgently need more precise UV sources, custom microcontrollers, better materials to fix inconsistencies, and we really need to figure out internal curing techniques. But even with those challenges, the trajectory of this tech is absolutely thrilling. So let me leave you with this. Given how fast this solid-state technology is advancing, will the next generation of space stations and naval vessels carry SVM printers to manufacture critical replacement parts right there on the fly? We are finally escaping the limitations of liquid printing, and the future of portable, hyper-stable manufacturing is literally solidifying right before our eyes. Thanks for joining me on this explainer. Stay curious, and I'll catch you in the next one.